OK, so in the last video, we talked about ASLR. ASLR was wonderful. It allows us to move the segments of memory around such that their absolute addresses change, although their relative addresses do not. And this makes it harder for the attacker to guess where on the stack their shellcode is. So when they write the shellcode, it's somewhere in memory, but they no longer know the absolute address. But just like all the other memory safety mitigations, there are some ways to subvert ASLR. So the two ways that we will talk about are leaking addresses and guessing addresses. So let me start with guessing, because that's kind of the easy one. Just like how you could guess the value of the canary, you can also guess the addresses of your shellcode. So when you write shellcode into memory, you don't know exactly the address of where you put it, but you can just try a bunch of times and guess until you get it right. And something that actually helps a little bit here is the fact that the randomization usually happens on nice boundaries. So it's not going to be the case that, for example, the addresses are not on multiples of 4 bytes. So for example, in all the addresses that we've seen and that you'll see in the project, the RIP will be at an address that's a multiple of 4. That's kind of nice. It means that the address is word aligned. So that reduces the amount of guessing you have to do. You know that the address is going to be a multiple of 4. More generally, if you remember something called virtual pages from CS61C, you'll know that there are also these things called page boundaries. And usually, the addresses will also be page aligned. So there are some things you can do to improve your chances of success. But ultimately, you are still guessing. And so even under certain assumptions that we won't talk about here, there are roughly 20 bits that need to be guessed. And whether or not 20 bits is possible, and you can guess 2 to the 20 times, depends on your threat model, like we talked about last time. And on a 64-bit system, under certain assumptions not covered here, you might have to guess roughly 2 to the 36 times. And again, whether or not that's possible depends on your threat model. And the other thing you can do to subvert ASLR is you can try to leak addresses. Because remember, the relative locations are not randomized. So it's always going to be the case that RIP is above the SFP, which is above the local variables. So once you have a single address of something on the stack, for example, someone tells you the RIP is right here. Well, then you can fill in all the other addresses. If the RIP is at address 30, then the SFP must be at address 26, and then the first local variable at address 22, and so on and so forth, just to give an example. Or for example, if you have an address on the stack and you can print out that value, that might give you a clue as to what all the other addresses are. For example, if you leak an address and it starts with an 8, that might be a good sign that all the other addresses on the stack also start with 8, to just give an example. So those are the two ways we can think of to subvert ASLR. Either reveal an address, which might allow you to find where everything else is on the stack, or just try and guess the addresses and hope you get lucky after a bunch of tries. So to give a concrete example of what leaking addresses looks like, let's say we have a piece of code like this. We'll not talk about it in too much detail, but we have some character array called buff. There it is. We let the attacker fill it in. And then we call vulnerable, which then calls printf on buff. So what's the problem here? We're calling printf. We're giving the attacker control over that very critical 0th argument. And if the attacker can control the 0th argument, they can perform a format string vulnerability. So if you think back to format string vulnerabilities, you might remember they allow you to print arbitrary things on the stack. So for example, if I provided an input like %x, what does that do? Well, then printf's going to think, well, here's printf, and the 0th argument was this one, so the first argument must be the one directly above. So I should match %x with this value. Even though we didn't actually provide an argument, printf will think that this is an argument and print this value out. And so to make a long story short, printf will allow the attacker to learn this value. And what is this value? It's an address. What is it the address of? It's the address of the previous stack frame's SFP. So by leaking this address, you might be able to say something like, I know this address, so this address must be the thing I leaked plus 4, and the address of secret must be the value I leaked minus 4, and the address of buff must be minus 24, and so on and so forth. So just by getting a single address, that allows you to find the addresses of everything else on the stack. And so for example, if the %x printed out the output BFFF0408, that tells me that the address, well, this value is BFFF0408, which tells me that this address must be BFFF0408 according to my diagram. So then the address of secret must be BFFF0404. And I can find other addresses on the stack because I leaked one of them. And this again relies on the fact that even though this entire stack could move up and down, so maybe right now it's BFFF, but the next time around the top bits are CFFF or something completely different, the relative locations will still be the same. So that's what this slide is showing.